Hello everybody, let us start lecture 55 and the course is on phase diagrams in single component and binary systems, and the topic what we will discuss is on the evolution of phase diagrams if the enthalpy of mixing, which is del H mix, varies for solid and liquid solutions. Till now what we have discussed is basically the effect of different values of del H mix on the del G mix, which is the Gibbs free energy of mixing for the formation of a solution, either solid or liquid solutions. We have not specified it. Okay. And we have seen that under different conditions, like when delta H mix is 0, when delta H mix is less than 0 or greater than 0 or extremely high positive values of del H mix, we see that there is a distinct change in the pattern of delta G mix. And in fact, some occasions we have also seen what will be the effect on the solution free energy, which is G 2. We have been talking about G 2. G 2 is always a solution free energy. That also changes. Now, we have taken a kind of simplistic approach stating that the two pure metal for the binary system A and B, we have taken their pure metal free energy as standard reference value, and that value is taken as 0. And that time we have seen that the delta G mix is same as G 2 for the solution. Now, what we will do? We will see that if there are possibilities of solid and liquid solutions both, and liquid as well as solid solutions both can have different values of delta H mix. It, of course, under ideal condition delta H mix would be 0 for both solid and liquid solutions, and we have seen how the shape evolves for the phase diagram. It was a kind of I shaped phase diagram, which is called isomorphous system. Now, what we will do? We will take different combinations, like let us say liquid delta H mix is 0, liquid delta A and then solid delta H mix could be highly negative or highly positive values. Similarly, we can also check if solid enthalpy of mixing is 0, considering liquid enthalpy of mixing to be highly positive or negative. Okay. So, those cases we will see a specific pattern of Gibbs free energy of the solution, as well as we will see when we try to understand the equilibrium of phases existing in the system using the common tangent rule. We will see that at different temperatures different phases will evolve, and those stability of those phases will be reflected in the phase diagram. And instead of having the phase diagram first, we will check the Gibbs free energy of the solution versus composition plot, and then we will try to take those equilibrium stability conditions using the common tangent rule and reflect it on the T versus composition plot. That will give me phase diagram. So, what we have done till now? We have seen that we are taking a regular solution model for treating non-ideal solutions, and we are making binary solutions with A and B. Okay. These are the two pure metals. Initially, let us start with pure metals and at a particular temperature and pressure, which is considered to be 1 atmosphere. So, pressure remains 1 atmosphere over the entire temperature regime, and in fact, we can change the temperature, and each temperature we will try to see the equilibrium conditions when the solutions are in solid or liquid state. Okay. Now, we are taking 1 mole substance, that means X A and X B are the mole fraction of two components, and when you add them together it gives you 1 mole solution. It could be liquid or solid solutions, and we have seen that delta H mix is given as omega X A X B, where omega can be 0, can be greater than 0, can be less than 0, can be greater than 0 or greater than less than 0 or greater than 0. So, that means highly positive, highly negative, all those values could be possible. And if I try to talk about solid solution, so solid solution can have everything to be solid. Similarly, if I talk about liquid solution, everything will be considered as liquid. Okay, like that way we can reflect. Now, similarly, we can have delta G mix, which is delta H mix, and here also I can reflect with solid / liquid, and S is considered for solid, liquid, L is considered for liquid. Here also solid / liquid minus T del S mix, it will be also solid plus / liquid. And in fact, del S mix is minus R x A ln x A plus x B ln x B, where if we consider solid, then everything should be considered as solid. And similarly, if we consider liquid, everything should be considered as liquid. Fine, all the compositions. And interestingly, this one does not change whether you consider solid or liquid at a particular composition. Okay, fine. So, that remains same. Similarly, for this also, at a particular value of omega, it will also be same, okay, because x A and x B are the mole fractions, and that does not depend on temperature or pressure, okay, because those are compositions. Now, with this consideration, this is basically gives free energy of mixing, this is enthalpy of mixing. Similarly, we can find out the solution free energy for solid or liquid, it will be G 1 plus delta G mix. Okay. And here G 1 is basically the unmixed condition, okay, the free energy of unmixed condition, and that time the mole fractions of pure A and B that will be considered, and it is a kind of weighted average is basically x A G A naught plus x B G B naught. And here if I talk about solid, it will be everything would be solid, and if I talk about liquid, everything would be liquid. So, that is what we cannot mix them, fine. And this value also with the change in solid and liquid, that would change, because these two values will change. We will see that, and we will take the same way what we have done while drawing phase diagram in case of condition where ideal condition is held, that means enthalpy of mixing is 0 for both solid as well as liquid solutions. And that time we have seen that the relative positions of these two values, which is gives free energy for pure A and pure B under standard conditions, which is pressure is 1 atmosphere, and we can take the reference value to be 0 as we have done previously, and that 0 value can change depending on the relative stability of A and B at that particular temperature, whether the solid is stable or liquid is stable depending on the temperature. So, that way we can also change the position of those pure metal free energies, solid and liquid, for both A and B. So, that is what G 1 would change also, G liquid, and this is solid / liquid, and hence G 2 would also have a variation depending on G 1 value, because delta G mix we are calculating on the basis of this particular formula, and at each composition that delta G mix also vary, G 1 also vary, and G 2 hence G 2 would also vary. So, we will see that those things as we go ahead. Once we know this, we can have several combinations. What are the combinations? Combination 1, we can have omega for solid equal to 0, omega for liquid equal to 0, and a combination 2, omega solid could be 0, but omega liquid could be highly negative. Okay. Combination 3, we can have omega solid could be highly negative than negative, but omega L could be 0. And combination 4, we can have omega S could be positive, but omega L is highly negative. Okay. So, let us consider only these 4 conditions, and as we keep having different combinations, the phase diagram would change. So, we will first consider these 4 conditions, okay, and then if time permits, we can have several other combinations. Fine. So, this is study these 4 combinations. Okay. And hence, we can also state that delta H mix for solid equal to 0 and delta H mix for liquid equal to 0. This gives me delta H mix solid equal to 0, delta H mix liquid less than 0, delta H mix. So, you just reflect the same information here. Okay. So, first let us try the combination 1. In fact, we have done combination 1 before, but only thing is, remember, I will just repeat that, so that for other cases and non-ideal cases, it will be easy to understand. Now, first of all, what you have to do? You have to see temperature, free energy temperature plot for pure metal. So, and remember, this is arbitrary, and we are taking conditions like this, which is G B naught, this is solid, G B naught, this is liquid, this is for, and this is the temperature, which is melting point of B, and then we are taking another one, which is for A, this is T M A, and this becomes G A naught liquid, this is G naught A solid. So, this will be my reference free energy for solid and liquid A and B, and here we are taking the B melting point is more than A, and the typical placement of those lines are arbitrary, remember, and these particular lines that is placed as per their Cp values of solid as well as liquid B and solid and liquid Cp values of A. So, if we take experimental values, these particular positions can also change. They can crisscross each other depending on the values of Cp's. Okay. But if we take this reference and if we take a different temperature, and different temperature, we will try to plot free energy versus composition for both solid and liquid, and accordingly we will choose our stability as per the common tangent, the way we have done for isomorphous phase diagram when we try to draw isomorphous phase diagram. So, let us choose this is condition, this combination 1 we are doing, okay. Combination 1, okay. And here we are taking omega S equal to 0, omega L equal to 0. So, that means this is ideal condition for both solid and liquid solutions. So, let us say I am choosing temperatures. So, now let us do for at a temperature, let us say I choose the temperature accordingly. So, let me choose one temperature here. another temperature at Tm, another temperature in between Tm and Tm A and Tm B. So, this is temperature, another temperature which is equal to Tm B, and one temperature which is beyond Tm B. So, let me mark them. This is T1, this is T2 and this is T3. So, at T1, if I try to draw this is 0 0, x b is varying this way for all the curves. B is on the right side, please understand that, and this is x b equal to 1 pure metal side, this is x a equal to 1 pure A side. Now, we have to see the stability. As we see that G B not solid is stable for in case of B at T1, this is at T1. We are doing for T1, and this side is G A not solid, and accordingly the position of G B not liquid will be. So, let us say this is G B not liquid and here it is G A not liquid. So, we have this is for, let us say I am indicating solid for green color and liquid for the solid G2 will be for with black color. So, this would be my G1 of solid and this will be G1 of liquid, and corresponding the plot for solid and liquid G2. So, this will be for G2 liquid, this is G2 solid. Fine. So, now as per stability over the entire temperature, entire composition range, solid free energy of the solid solution free energy is lower than liquid solution free energy. So, the solid will be stable over the entire temperature zone. So, if I try to plot temperature versus composition, this is temperature, this is at temperature T1 and here everything would be solid. Okay. As per the stability. Now, let us do it at T equal to TMA. Please mark the lines accordingly. This is GB not solid, of course, this is 0 0 point. This is GA not solid, which will be equal to GA not liquid, because this point at this point X A equal to 1, both solid and liquid free energy merges for pure metal A, and liquid this should be GB not liquid. Okay. Now, I can have the liquid line, this is G1 liquid and this one would be G1 solid. The solid free energy I can draw, and liquid free energy it will merge here, this point it will start. Okay. And we see that at T, this is the temperature I am talking about. TMA. So, there at this location we have both solid and liquid equilibrium, the pure metal A side, and rest of the places we have solid to be stable. Okay. Rest of the places, all the other composition, solid solution would be the stable, because solid solution G2, this is G2S and this is G1 liquid. G1 liquid is having higher free energy as compared to G2 of liquid, that is gives free energy for the liquid solution, has higher free energy as compared to solid free energy, solid solution free energy G2 solid over the entire composition range except pure metal A. Okay. So, that means at X A equal to 1, we have both solid and liquid A would be having same free energy, and both can be as per the stability part, both can be coexisting. Now, this is at temperature T equal to TMA, and you please put other stuff X A equal to 1, X B equal to 1 and X B varying this way. And of course, this axis is free energy axis, this is axis is free energy axis. Now, let us plot at T equal to T2, and one more observation, please understand that you can draw it as per that. If we increase the temperature, we will see that del S mix minus T del S mix will go farther down and it will be steeper convex downward. We have seen before, because del S mix does not change, but once you multiply T and there is a minus sign. So, it will be farther steeper and it will be steeper downwards. Okay. So, accordingly G2 lines also will be little steeper than that at lower temperatures. So, you can adjust that accordingly when you draw at your end. Okay. Now, if I take at T2, we see this is 0 0 and this reference point we can consider for still G B naught solid would be considered as 0 and G A. Now, G A liquid would have lower free energy as compared to G A solid. So, that is what we can put G A naught liquid to be 0, that reference value we can assign that. And here we will have G B naught liquid, and here we will have a situation we can have G naught A solid would have higher free energy as compared to G A naught liquid. So, accordingly we have placed them. So, now we will first connect liquid line with G1 line for liquid. This should be my G1 line for liquid and this will be my. So, let me draw it with a solid one. This is G1 solid and this one G1 liquid. So, G1 liquid can be G2 liquid we have to draw. This will be G2 liquid and G2 solid is this. This is G2 solid. Now, we see that we can have a common tangent. So, the common tangent passing through fine. So, this is the common tangent and we see at this locations G B bar of solid equal to G B bar of liquid and at the on this other side G A bar solid equal to G A bar liquid. So, that is indicating equilibrium and the equilibrium compositions are these two. This is X B of solid and this is xB of liquid. Okay. And this is temperature is T equal to T2. So, now at T2, this is at T2, one composition, the same information, those compositions will be just taken to T versus xB plot. So, this is the point which indicates xB of liquid, and this is the point which indicates xB solid. Okay. Those are the two equilibrium points. And if we take different temperatures in between two melting points of pure metal A and B, we can have adjustment in that you can actually have that common tangent will shift either left side or right side depending on which side you are taking. If you take temperature below T2, but still in between two melting points, these equilibrium points will shift towards left, and if you take temperature beyond T2, still in between TMA and TMB, that those two equilibrium points as per the common tangent will shift towards right. Okay. So, now if I take a temperature, now this is again, please consider that these information and xB is varying this way, okay, and all the compositions are placed as per with reference to B. Okay. Now, we take a temperature T equal to TMB. The TMB, so that means at this particular temperature, this temperature, if I take TMB and xB 1, xa equal to 1, 0, 0, those reference values, this can be taken as GB naught solid. The same place I can take GB naught liquid, because the free energies of solid and liquid pure B, they have the same free energy at T equal to TMB. But here GA bar not liquid will have lower free energy as compared to solid A. So, this can be taken as reference value to be 0, and then solid A would have, liquid A would have placed here, the solid A would have placed here, because you see at this temperature we have solid gives free energy of pure A has higher value compared to liquid pure A, that free energy value. Now, then let me just connect, this is solid, solid is connected with the, let us say, black color, this is G1 solid, and the liquid would be here. So, T equal to TMB. Now, if I draw, and this is G2 solid, G2 of solid, and then G2 of liquid would be. Okay. So, you will see that at T equal to TM B, we will see at this point, we have solid pure B and liquid pure B would be having same free energy, and all other compositions xB is this way is varying, all other compositions we see that the liquid solution free energy, this is G2 liquid solution free energy is lower than G2 of solid. So, all other compositions at that temperature TMB, liquid will be stable, but at pure metal at composition xB equal to 1, pure B solid and liquid both will be coexisting, okay? Their stability would be similar. So, that means we have this point, and if we connect them, so once we connect them, we will get a curve like this. Okay. So, this is the isomorphous phase diagram what we have seen. Now, once we increase the temperature further, which is at T 3, okay, T 3 T equal to T 3 which is more than the melting point of B, that case we will have here G B naught liquid will be having reference 0 value, G A naught liquid this is G A naught liquid will have 0 value, this is 0 0 values, okay. And G A solid would be here, G A naught solid would be positioned here, and then G B naught solid will be positioned here. So, now this will be G 1 of solid, this would be G 1 of liquid, we missed this point here, G 1 of liquid here. Okay. And then if I draw the G 2 line, this would be G 2 for liquid, this would be, this is G 2 of solid, this is G 2 of liquid. Now, we see at a temperature T 3, let us say this is my T 3, everything would be liquid solution. Okay. And in between that I, we have solid plus liquid solution. So, why? Because at T equal to T 3, over the entire composition range, liquid free energy has the lower value as compared to the solid free energy when we have solution free energies under consideration. Okay. So, now that way that particular phase diagram, isomorphous phase diagram evolves. Isomorphous phase diagram evolves. So, why we have repeated this? Because now this particular thing would not change. The relative positions of pure metal A and B and their free energies, and we will just keep changing the temperature, and now we see how the shape of solid and liquid free energies make a change on the phase diagram, rather make a change on the equilibrium phases that could exist, and also correspondingly what will be the shape of the phase diagram. Okay. Now, let us do the combination 2, this is combination 1. So, we will be doing combination 2. So, combination 2 what we have considered, omega s equal to 0, omega L less than equal to 0. Okay. So, that means liquid has higher is highly negative as compared to. So, solid is ideal, you can say this is ideal, but this is non-ideal. So, liquid solution is non-ideal, but solid solution has ideality. Now, that case, that situation will just carry the same operations here, but only thing is, let me just explain this part first. Now, if I try to draw at a particular temperature, let us say temperature is T m A is less than T m B, and the temperature what we are considering T, which is greater than T m B also. Now, at temperature T, if I try to plot solid and liquid free energies for these two conditions, where I will keep the liquid and solid pure metal free energies unchanged, this is G A naught solid, this is G A naught liquid, this is G B naught solid, this is G B naught liquid. So, this temperature is TMB and this temperature is TMA. Now, I am considering a temperature here. Okay. This is the temperature we are considering. Now, at that temperature, what will be the relative positions of delta G mix as well as free energy of liquid. Now, and we will be doing it on the same plot. So, then only after that we will do it at different temperatures. So, if I try to see these are 0 points, x b equal to 1, x a equal to 1 and x b is varying this way and we are doing it at temperature T. Now, at temperature T this would be G b naught liquid, this should be G A naught liquid because that can be considered as 0. So, that is what we have taken this to be 0 and at that temperature del S mix or rather minus T del S mix would be R T x a ln x a plus x b ln x b. So, this one let me draw it with a different color, we will do it with this color. So, this is the one, this is minus T del S mix and that will not change for whether we consider liquid solution or solid solution. This contribution will be same on delta G mix as well as G 2. So, delta G mix would be equal to delta H mix minus T del S mix. So, this one would be same. So, this one would be changing. So, in case of liquid solution this will be taken less than 0 for liquid and equal to 0 for solid, that will be only change, but this will remain same for both liquid and solid solutions. So, let me draw delta G mix for both and liquid and solid solutions, but since now for solid solutions this will be my delta H mix since omega equal to 0. Now, if I draw liquid, this is for solid. For liquid, let us say this is highly negative. So, this is delta H mix for liquid omega less than equal to 0. Now, if I try to plot delta G mix for solid, so delta G mix solid will be actually lying on the same. So, I am just putting a dotted line, it will be little away from the T del S minus T del S mix just to indicate the position, but they are actually merging. So, this is equal to delta G mix for solid because this value equal to 0. But if I try to plot delta G mix for liquid, so that will actually go further down because that case this one and this one are to be added together and both of them have negative values. So, they will further go down, it will be steeper downward and it will be a convex downward plot, but much steeper than del G mix S or the solid solutions. So, that plot would be, we have just added them. So, this is delta G mix for liquid which is nothing but delta H mix which is nothing but this formula, same formula. Okay. Now, accordingly we will have a variation in the G 2 lines also. So, G 2 line for liquid for solid. So, now we have to see the position of G 1. So, G 1, so this should be let us say position of G naught B solid and let us say this is the position of G A naught solid. Why this gap is little more than this? Because you could see that this particular gap is increasing as we increase temperature, and this gap corresponding temperature is little lower. So, this is as per this arbitrary diagram. Okay. You can make changes as per your wish, but still things will be same. Now, if I try to see G1 line, so G1 line for solid is actually this one, solid is this, and G2 G1 line for liquid is this one. So, I can do it with the green color. Okay. This is G1 for liquid. Now, G2 for liquid would be same as this one. So, this should be nothing but G2 liquid, okay, because I see that G1 liquid is at 0 position. So, that time, since we know that G2 equal to G1 plus delta G mix. So, now G1 in this case liquid is 0. So, liquid this would be equal to this. Okay. So, G2 liquid, but G1 G2 solid will change, because G1 has lifted upward. Why? Because of this typical positions of pure metal free energies. So, G2 solid would be, I will do it with a different color. Let me take red color. Fine. So, this will be G2 solid. Okay. Now, you see how the relative shapes are taking up. For G2 liquid, it is much steeper than G2 solid, and that will have a difference, that will have the situation would entirely change as we change the temperature, and as we draw this G2S and G2L line and then see their free energy hierarchy as well as equilibrium, and we will now see how the equilibrium at different temperature varies and how the phases are appearing. Okay. So, I just wanted to show this just to indicate what will be the relative shapes of solid and liquid solutions free energies. Okay. Now, let us go and then see how the equilibrium would change. This is the reference. We will just have to draw that reference just to give G free energy, G as a function of T, and please understand that whatever we are doing now, this particular axis is free energy and this horizontal axis is composition. So, that is what it is, G versus composition plot, and previous case, even if I have not given that indication, please do that, okay, even if I have missed it. So, please do that. The vertical axis is free energy and horizontal axis is composition. That is what it is given, is basically called free energy composition plot. Okay. We will do it this way. So, this is for G B naught solid, G naught B liquid, this is G A naught solid, this is G A naught liquid, and this temperature is Tm A, this temperature is Tm B. Okay. Now, we have already seen one plot which is at T. So, we can take this information, and here at T we see that liquid is stable at all temperatures, because liquid free energy is lower than the solid free energies. So, if I try to plot temperature versus composition, this is x b, x a equal to 1 and this is x b equal to 1, and this is temperature at T, we see everything is liquid solution. I will just put L. Okay. Now, let us do at as we decrease temperature, let us do, this is the T we have considered. Let us see what happens here. This is T equal to TMB. Let us do that plot. This is GAB naught S equal to G naught B liquid. This is a reference 0 value, and here it is ZA naught liquid 0 value, and this point is GA naught for solid, G1 of solid, XP is varying this way, XP equal to 1, XP equal to 0 or X equal to 1. Now, the liquid G1 is, this is G1 liquid. Now, if I draw the free energy of liquid and solid solutions, liquid would be steeper, fine. This is G2 liquid and G2 solid. At T equal to Tm, we will have this point where we can get both solid A and B will be coexisting, their stabilities are same, but all other compositions liquid will have stability. So, it will still be liquid solution all over the other compositions. And remember, the relative steepness will gradually decrease of those G2 lines. Why? Because temperature is decreasing. So, minus T del S mix contribution will be felt less. Okay. Now, let us say I do a temperature at this. Let us say this is T1. So, this is T1. Now, at T1 let me draw that. T1, now GB solid would be stable. So, that is what GB solid is taken as 0, and GA liquid is still stable, and this is GA solid, and this point is GB naught liquid. Okay. Because T equal to T1, which is below melting point of B, solid B would be stable. So, now this is G1 solid, this is G1 liquid. Now, we have a situation. So, first let me draw G1 liquid. So, G1 liquid, since delta H mix is highly negative, so it will be still steeper as compared to solid. So, it will be having a plot like this, and now G2, this is G2 liquid. Let me just plot the G2 of solid. G2 of solid would be this one. So, this is G2 of solid. Now, we see we can actually have a common tangent. So, the common tangent if we draw, so the common tangent let me draw, and these common tangent will meet somewhere on this axis. Okay, so, there G A bar of liquid equal to G bar A of solid, this location, and at this location G B bar solid equal to G B bar liquid. Okay. And we see that we will get two compositions. This is XB of liquid and this is XB of solid. These two compositions can have coexistence because that is falling on the common tangent between liquid and solid solutions free energy, and then at that temperature, this is at temperature T equal to T1, those phases will be stable. But if you take a composition XB composition to the right of this, solid will be stable, here solid will be stable, and left of it liquid would be stable, and in between we have solid and liquid of two compositions of this one and this one, they will be stable. Okay. So, now we can actually drag those two equilibrium points over T1 in T versus XB plot. So, this is one point, this is another point. Okay. Fine. This point corresponds to XBS, this point corresponds to XB liquid. This is still we can put on the till on the little left side, this is here. Okay. Fine. So, so the in between this XBL and XBS, we have both solid and liquid, they will be coexisting, those will be the solution and their compositions will be XBL and XBS. In between compositions we cannot have any composition we take which is in between these two compositions, they will segregate into two phases of composition XBL and XBS. Now, we take further down, let me take it to a temperature which is T equal to TMA. So, we take this one. At this compositions, let me see how the curve shapes. So, this is G this way, G this way. This is G B not here solid, and this is G B not liquid at T equal to TMA. You see the relative positions of the pure metal free energies. Okay. And this will be G A naught solid as well as G A naught liquid, and this point is 0, this point is 0. XP is bearing this way, XP is bearing this way, XP equal to 1, XP equal to 0, XP equal to 1, XP equal to 0. Now, the liquid line G1 line is this one, this is G1 liquid, and G1 solid would be this one, G1 solid. Now, let me draw the line. G2 line still steeper, 2 solid, this is G2 liquid and G2 solid. So, one point will start from here, it will be symmetric. Fine. This is G2 solid. Now, we see we can have a common tangent, this one. So, this is XB L XBS. Okay. So, at T equal to Tm A, I see that the liquid line is moving towards left and solid line is also moving towards left, okay, as per this particular common tangent. So, if you can extend it, so this side G A bar solid equal to G A bar liquid, and this side G A bar G B bar solid equal to G B bar liquid. Okay. Or I can, so this one changing the notations, because the superscript is considered to be the phase. So, let me also change this notation. Here also you can change, it is just about your convenience. Okay. So, these 2 points are placed here, but still at t equal to T m, I am seeing that liquid and solid solutions are coming up all the way to T m b. Now, let us do it at a temperature below T m a. Let us say this is the temperature T 2. So, I am putting the line, this is T 2. Let us do at T 2. 0 0, this is G naught B solid, this is G naught A now it will be also solid, those will be 0 values, this would be G A naught liquid, this would be G B naught liquid. Okay. At T equal to T 2, the temperature is below T m A as well as T m B, hence both cases solid A and solid B will be stable. So, that is what those values are taken, those free energies values are taken as 0. This would be G 1 liquid and this is G 1 solid. Let me draw first the liquid one. Okay. This is G 2 liquid, and if I draw G 1 G 2 solid, now one interesting situation will arise. You will see the G 2 solid, when we drew it, it will start from this point. Okay. This is G 2 solid. Now, interesting, till now, till T equal to T m A, we had only 2 points, composition points where common tangent can be drawn. Now, we have a situation where 2 common tangents can be drawn. Okay. One common tangent is going through like this. Okay. So, that gap is visible now. So, this one, and then you extend it this other one. This is G B bar of solid equal to G B bar of liquid, and here G A bar of solid equal to G A bar of liquid. This is one common tangent. The another common tangent is coming here. This is another common tangent which is going through this. If we extend it, so this point, this is the composition and this is another composition, and here we have one composition here, another composition here. So, this is X B of solid, this is X B of liquid, but on the other side we will also get 2 compositions, X B of liquid and here X B of solid. Okay. And here we have G A bar solid equal to G A bar liquid, and at this location we have G B bar solid equal to G B bar liquid. Now, this solution model, that regular solution model has been taken up. So, that is what we have considered one assumption, that both have same crystal structures. So, that means the solids on the both sides which are coming due to the common tangent rule, those are the stable phases of solid of composition X B S. In order to make difference in these two compositions, and since they are of same crystal structures, so it is generally given as the phase, the left side phase is taken as 1, right side phase is taken as 2. Okay. So, S 1 and S 2, and here also S 1 and here also S 2, this is S 2, this is S 1. So, just to give a difference, just to indicate differences between these two phases, because those are two distinct phases. Please understand that though they have different same crystal structures, but their compositions are unique, and phase definition is chemically homogeneous, physically distinct portion of a system. Okay. So, that is what those are two different systems, two different phases. And the liquid also, if you see, since liquid has a huge possibility of mixing together and they have no crystal structures as of, if we understand that way. So, both the liquid compositions, we can indicate those both the liquid compositions on the phase diagram, but they can be taken as a part of the same liquid. Okay. So, that is what we are not putting any 1 or 2, but left side liquid composition is in equilibrium with S 1 solid, and the right side liquid composition in equilibrium with the composition of S 2. Okay. Now, at T equal to T 2, please understand that TMA, fine, we have taken that, and TMA we could see that at TMA we have TMA liquid, G naught A liquid and G naught A solid, both have the same crystal structure, same free energy. So, that is what there will be existence of pure A solid and liquid. So, this particular point pure A, both solid and liquid, both will be having same free energy. So, there will be 3 points. This point corresponds to X B S, this point corresponds to X B L, okay, and this point corresponds to, this is the point corresponds to this pure A solid and liquid, and here this point is pure B solid and liquid, both have the same thing, same free energy, solid and liquid, pure B. Now, at T 2 we see that the right side compositions are shifting towards left and the left side compositions, two equilibrium compositions are now appearing. Okay, fine. So, this is X B S 1, this is X B L, this is X B L, and this is X B S 2. Just to indicate difference, till now we have put S, now we are distinguishing those two solid phases, those are actually coming up due to equilibrium conditions. Now, still if I go down further, let me draw it here. So, this is T equal to T 2 and I am going down further the temperature scale. So, let us say I am putting a temperature here, T equal to T 4. This is T 4. Okay. This one was T 2, this one was T 2. At T 4, we can have a situation like this. This is 0 0, X B equal to 1, X B equal to 0. Even if I miss that, please put that G, this is G versus composition plot, and X B is varying this way. Okay. X B G, this is G B naught solid. Now, this gap would extend, G B naught liquid, and here also the gap will extend, G A naught liquid, this is G A naught solid. Okay. Those will be taken as 0 values. Now, this would be my, this is G 1 solid. So, G 2 solid, I can put this way, and we can have a situation like this. So, this is G1 of liquid. So, I can have a typical situation like this. So, just change that, because after T2 we should consider T3 rather than T4. Okay. So, at T3, let us say this is T3, fine. At T3, we see that it is actually at some locations like this. You have to just make that adjustment. It will be, let me just do that adjustment. This is G2 of. So, this point both are merging. So, right side solid will be stable, left side solid will be stable, and in this case right side solid, left side of this solid, in between these two solid plus liquid, and whether I can put 1 and 2. This is in between S1 plus liquid, in between we have S2 plus liquid. Okay, like that way you can put all those equilibrium conditions. So, right side of this will be solid, left side of this will be liquid, because we have to just check which one has a lower free energy. But at T equal to T m A, at this location we have both solid A and liquid A will be coexisting. So, now this is that point where we have both solid and liquid solution will coexist under equilibrium. Now, this is interesting, at this location both solid 1 and solid 2 are merging, okay, fine, solid 2 are merging. So, now this point can be considered for both solid 1 as well as liquid solid 2. Now, we will just connect all those solid 1 lines, liquid lines for both, and solid 2 line and liquid line. If we connect them, we will get a typical plot like this. This one, this. So, we can adjust these points accordingly. So, this point is coming here, we will adjust that. So, it will actually fall there. So, now here also if you connect them, let me do it with a pink color, and here also, fine. So, now you see that the curve, when we considered the condition we have considered a combination 2, we are getting 2 I shaped plots. And when we talk about, when we see combination 1, we had only 1 I shaped. Now, here we can mark them. So, this is liquid, this part, this particular I, in between this I we have solid plus liquid, and I can put solid 1 and liquid, and here we have solid 2 plus liquid. These are the stable phases. And once we go further below the temperature, let us say I am taking a temperature which is below this, okay, this is T4 now. So, that T4, if I draw that free energy composition plot, this is T equal to T3, and now T equal to T4, this is G B naught solid, this is G A naught solid 0 0, this is G 1 solid, and now it will further go up. This is G B naught liquid, this is G A naught liquid. Okay. So, this is my liquid, this is my liquid G 1 liquid. So, this axis is G, x b is varying this way, x b equal to 1, x b equal to 0. So, now if I plot G 2 for liquid, this is G 2 for liquid and G 2 for solid would be, this is G 2 for solid. So, you see that over the entire compositions range at T equal to T 4, solid solution free energy is lower than liquid solution free energy. So, the solid will be stable once we go below T 3. So, that is what here we have only solid phase, here we have only liquid phase, and in between those two eyes we have solid and liquid, both are both will be having their existence. The final plot is becoming like this: x b equal to 1, x b equal to 0. So, let us say this is T m A, this is T m B. So, here is that point, we have one I and we have another I. Okay. So, this is liquid, this is solid, and here we have solid 1 plus liquid, here we have solid 2 plus liquid, okay, and this is the temperature. So, this is the phase diagram, typical phase diagram we will experience when omega s equal to 0 and omega liquid is less than 0. In fact, as we, so what do you mean by omega liquid less than 0, less than 0? That means the liquid line stability is much higher than the solid line stability. So, the more the negative value of this particular point will further go down. So, that means liquid stability will go up. Okay. So, more the negative value of omega L, higher will be stability of liquid solution of liquid. Okay. So, this particular information will be very tricky. We will use this particular information while seeing eutectic phase diagram, and eutectic phase diagram will have typical there is a kind of typical nature of this and we will see it later. Okay. So, we have considered two conditions, one is combination 1, both the omega values of solid and liquid solutions are 0. Another combination is when liquid solution has much negative omega L, where a solid omega L is 0. So, that condition we see two I's are coming, actually combination of two isomorphous. Okay. So, in fact, if we draw a line like this, one isomorphous is forming this way, another isomorphous is forming this way. Okay. So, let me stop now. So, we will, and please practice it. If you do not practice, it will be difficult to understand. Just show this, see this, keep seeing this, and then try reflecting the equilibrium compositions over this temperature composition plot, you will see the phase diagram. Okay. So, let me stop here, we will continue our discussions on the plotting of phase diagram or the evolution of phase diagram under two other combinations in our next lecture. Thank you very much.